Yeah. Thanks for the introduction. Today I'm going to talk about a particular type of active particle having these properties. By the way, this can be, naturally available like living particles, as well as they can be engineered in a laboratory. Okay, so the problem statement start with this observation from experiments done on a active particle which is fairly rigid, as well as almost like a round shaped object. It's a microorganism named Chlamydomonas. And when these are put in a channel with some flow, imposed flow, in normal conditions, they follow just the streamlines, as you can see from here, and the densities are uniform across the width. But when a light source is turned on and when these particles like to orient towards the light source, they get focused, they migrate across the streamlines and they get focused across the near this central region. So the basic mechanism is the following. Because the flow is not uniform, there will be fluid vorticities turning the object in this way, and that will also turn the self-propelling direction. And because of the interplay of the flow field, what you will have is a oscillatory trajectory. And when the light is turned on, there is a competing torque, and then you will have a steady state orientation towards the center. But the main message is that without the external field, there will not be any cross streaming. That is evident from here. And that is also was seen from theory. You can see that the trajectory is oscillatory without the light source. That was done. This theory is for a particle which is round, but that can be extended for elongated objects like this. And again, the trajectory is flat, parallel on an average to the central surface. No, this is active. Active, yes. So the considerations done here are that the particles are rigid as well as symmetric. So there is a intrinsic polarity due to self-propulsion, but physically the particles are head-tail symmetric. Okay, there is no asymmetry. And one major point is that the active flows that are generated because of the swimming nature is not coupled to the motion. Okay. But this is, we asked what happens for this kind of particles, which flagellated particles. You can see that they are head-tail asymmetric, as well as the flow created by the head can affect the tail, which is flexible as well. Okay, so that's what we are asking in this talk. And the flows are ubiquitous in nature, so you cannot avoid that actually. And this question that we are asking, it could be, biotechnologically relevant, as well as it could be important in biological processes. And more than that, it is also interesting physics-wise. Okay, that's why we're tackling it. So our approach is, we took few steps to reach that modeling. I'm going to go through very quickly because of the lack of time. Can I point this? Yeah. Okay. Thanks. So at the first point, so this is the organism that we want to model. We want to model the hydrodynamic flows around it. The simplest model is, of course, a force dipole, and the flow field of this object and this object will be very similar when you are far away from that object. So when you start approaching the object, you will feel the extended nature of the object. So what we did, we said that instead of putting this force directly on the fluid, we apply that on the cell body, and that the movement of the cell body will actually transfer that force to the fluid. Okay, that's the model. Then we can solve for the self-propulsion velocity, and we can see that the flow generated by the flagellar force, the tail force, significantly reduces the velocity of the object. So once you know the velocity, you can calculate the flow around it. So there are various contributions. I'm not going to go into details, but you can generally, calculate calculate it with fair detail, and you have to introduce hydrodynamic image fields to satisfy the boundary conditions here. And then if you take into account the hydrodynamic image fields as well as the other contributions, you add up all of them, then you get an exact solution for the flow field around the swimmer. And once you know the flow field, you can put in another swimmer to get the hydrodynamic interaction. That's all been done for this particular model. Then my student Derek, he has improved that model with two steps. The first step is that he has allowed a bending of the flagella. That can happen in a dense suspension like this, for example. That makes the model non-axisymmetric. Fortunately, The non-axisymmetric part can be broken down into 3 different parts. One axisymmetric, which is already solved, and one non-axisymmetric part, which is messy calculation but can be done, and one active rotation. So if you add all this part, then he actually had an exact solution of the flow field of this case as well. So that being done, I am skipping some parts here, but the next step, which is like even more complicated one, is to introduce a physical flagella in the form of a slender body. On top of it, I mean, so these are the equations. I mean, I'm skipping lots of details. These blue ones are the flow field. Okay, so we are including the flow field created by the flagella, created by the cell body movement, and also the imposed flow and the distortion of the imposed flow because of the extended nature, and everything is calculated. One important point is that the flagella can be restored. There is a restoring torque, and the spring constant, if it is too high, then this system is axisymmetric. If it is small, then it is quite flexible. Okay, that's the model. It's quite detailed model, but once we have it, we can put it in the imposed flow. Say we took it to be the Poiseuille flow, parabolic flow, which is typically created between two walls. So apart from that fact, we do not have any other contribution from the walls. Okay, so so then we put the swimmer somewhere there, and then we found that the trajectories are still oscillatory, but they are now quite sharply deviating towards the wall. So note that this deviation is quite sharp compared to the body size, because this length is scaled with respect to the channel width. Okay, this is quite significant. So we have a sharp cross-stream migration even without external orienting field. And that means that the particle likes high shear rate region. That typically means that the particle likes to go towards the wall. Okay, that's the interpretation. 2 points. If we have a symmetric but passive particle, we don't see that, as well as active but symmetric that we discussed earlier, we don't see that. So both are flat curves. So the key aspect here is activity plus asymmetry. Okay. So now we wanted to dig into the physics. I mean, Dirac actually simplified those calculations to went to this limit. I mean, although I say simplified, this is really non-trivial calculation. But this is the analytical result of the rotation angle, angular velocity as a function of theta, and you can see that the particle stays longer time in the upward direction here. So because there is an asymmetry, this is coming from the asymmetry. Okay, so that is analytical calculation. This is from the full simulation. This is in the center of mass reference frame, and if you plot that for rigid particles, you can see that the plots are very similar. For flexible particles also, I mean, you can see the asymmetry. Okay, so the basic physics has been captured. So, but more than that, I mean, so there is a rich dynamics that we
2+2.
Okay, thank you. We discovered here. So if we are far away from the center line, the particles always go to the wall. But if you're near to the center line, the particles are able to cross the center line, and then you see the oscillatory trajectory with a growing amplitude. Okay, we have a physical explanation for that. But then at some point there will be a bifurcation, and the particle either goes to the upper wall or the lower wall. And the rotational dynamics is also very interesting, because the vorticities on the either side is different. The particle starts to oscillate like that with the growing amplitude, and at some point it oscillates actually entirely in one part, and it actually goes to the wall there. Okay, so and that's the trajectory in the left frame, from the left frame. And what we observe is that sorry, there is a physical explanation for it. I'm sorry, so I should have played the movie. So you can see it's growing, and then there will be bifurcation, and yeah. Okay, then it goes like this. Yeah. Okay, so I'm skipping the physical explanations. So what we observe is the signature of chaotic nature. So it really depends upon whether particle will go up or down, depends upon the initial condition, in the initial height. Then we, I mean, scan this phase space. We saw the same thing, that most of the cases, depending upon different orientations and different flexibilities, different heights, most of the cases particle like to go to one wall or the other. So then we can put into this external field mimicking the light, external light, and then the observation is that without asymmetry, this is the curve. Okay, so this is how the particle comes to the center. With asymmetry, the approach to the center is quite fast. Okay, quite sharp. Okay, so then we can do interactions between two particles, and we can go to a bound state where the circularly rotating trajectories are observed. These are very similar to these trajectories which are observed in our institute in Kumar lab. and with artificial microswimmers. Okay, so we just I'll take like half a second. So we now put these particles in near a wall. So these videos are a little bit older. We have put physical flagella as well as rotations of the rotation and counter rotations of the particle, and we have got very interesting results of hydrodynamic trapping. So, but that is a story of another day. So with that, I thank the organizers for giving me the talk. Yeah, and then my collaborators, funding from SCRB, DFG Germany, and IJR Tirupati, and I thank the Param Brahma computational facility from Pune, IJR Pune. So these are some other works that's going on in my group, and if you are interested, then I'll be happy to talk about that. Yeah, thank you for it.